Hello, we had been studying quantum mechanics and the basic postulate of the quantum mechanics, and the final one was the time evolution of the state, which is represented by the Schrodinger equation. Today we will further analyze the nature of the wave function in the first part, and then we would rather like to go into the mathematical intricacies of the operators, in particular the Hermitian operators. Okay, so we know by now that the Schrodinger equation is given by IH cross del psi del t is equal to H psi, where H is the Hamiltonian operator and the left hand side IH cross del t is the energy operator, and this is called the Hermitian operator. And the first question which arises is that this psi, which is a simultaneous function of x, y, z and t, this is in general can be written as r of t, vector r of t. This equation is a second order linear differential equation, and this must satisfy a solution which would be again linear. So any linear combination of psi 1, psi 2, psi 3 could be a new psi, which we have learned in our differential equation course, and that is very much in agreement with the fact which we have seen in our double slit experiment, that if you have two psi's, psi 1 and psi 2, then a linear combination of psi 1 and psi 2 is again going to give us a new wave function. Now the question is that for any value of any arbitrary value of psi, if this particular equation, which is known as Schrodinger equation, is satisfied, then is that psi a possible wave function for a given physical system? Then we have to see the exact admissibility condition. There are certain mathematical admissibility conditions which are to be applied to make the psi to be physically plausible, physically applicable to real systems. And what are those admissibility conditions? The first one, or in general, there is the psi must be a finite one. So wave function psi must be finite, single valued, and continuous. The wave function must be continuous, psi and their derivative. Since why the derivatives also? Because the momentum which is represented as a differential operator is nothing but minus of IH cross del x in one dimension, and in three dimension it is minus of IH cross del. So del psi del x is also finite. In one dimension, del psi del x is also single valued, and del psi del x is also continuous. So the admissibility condition, mathematical admissibility, which particular psi is going to be a psi of physical importance satisfying the Schrodinger equation, must obey these three admissibility conditions. So the take home message for this part is both psi and its derivative must be finite, single valued, and continuous. So this is the first thing we need to learn for really starting up with the problems of quantum mechanics. Now, let us consider a simple problem. Suppose we have a particle moving in a one-dimensional potential well of width a 0 to a, and the corresponding wave function is given by psi x is equal to a sine n pi x by a. Now, suppose we want to solve this problem, we want to find the normalization constant for this particular wave function. Then what we need to do, we know that this particular wave function is continuous, finite, single valued, and their derivatives are also the same, and then we can calculate the value of a. So if we want to find the normalization constant a, what we should do is apply the normalization condition 0 to a psi star psi dx is equal to 1. So that gives us a square sine square n, where n is an integer. Okay, it can take value 1, 2, 3 and so on. N pi x by a dx 0 to a. So for a complete cycle this is a square a by 2, half of a. For a complete cycle the value of sine square is half of the interval, so that gives us a to be equal to root over. So this is first problem where we can calculate the normalization constant. Okay, and now if we want to have an idea, certain mathematical idea about the commutator, we remember that we have commutators as operators which can be written as a b, which is given by operator a, operator b minus operator b, operator a. Now, what is the physical significance of such commutator? That if a commutator is operating on a wave function, why should a commutator operate on a wave function? Because it is going to give us the physically observable quantity. Suppose you have a operator a which operates on psi, then if it satisfies the eigenvalue equation a psi, capital A cap psi is equal to small a psi with eigenvalue a, then, and the psi is the corresponding eigenvector or eigenfunction of the a operator, then we say that small a is the observable, physically observable quantity. So if a psi is a psi, then we say this is the physically observable quantity, because we know from our previous studies that this is nothing but equal to psi star a cap psi dx divided by psi star psi dx, which is equal to a. So the expectation value of a is small a. Now if we have two simultaneous operators which are a and b, which correspond to certain physical variable, and they are operating in such a fashion that first b operates and then a operates, or if it operates in the reverse way where first a operate and then b operate, then are the result the same? It may happen in quantum mechanics, that even in classical mechanics also, this is called Poisson bracket, where you do not get the same result if you alternate or if you exchange the operation of an operator of two operators. Let's see how. Now if a, we can write this as psi psi psi. Okay. Now this may not be in general equal to 0, and that's where we come, or that's where we actually arrive at the fact that we have commutator non-zero commutating variables. Okay, Let us try to see first of all see the mathematical examples, and then we will see the corresponding physical counterpart. Let us start with a very simple commutator. Let's say we have a commutator x and ddx. Okay, say x is a operator which operates on psi, giving x psi, and ddx is going to give us d psi dx. So if this operates on psi, then we have x ddx operating on psi minus ddx operating on x psi. So what does it give? It gives us x d psi dx minus psi minus x d psi dx. So these two cancels out, and this. So what we can say is that this operator for any arbitrary psi, this is valid for any wave function psi. So this is equal to -1. Now if we multiply the left hand side and the right hand side with minus IH cross, multiplying both sides with minus IH cross, what do we get? We get x minus IH cross dtx to be equal to minus IH cross, which is basically the momentum operator. So this is the physical counterpart of this particular commutator, which gives us that the commutator of the position and the corresponding momentum gives us minus of that. The commutator of x dx operator is minus of IH cross. And now I would like to do as your homework another operator, which is something like prove that for del 2 del x square x to be equal to 2 of del x. Okay, so just multiply both sides on the right hand side by an wave function psi, and then do the commutator. First multiply with this x, and then you can always, so this is given as an assignment, do this for you on your own, find the answer. In the same fashion, we can further prove that if we have an commutator of Lx, Ly, or before we do that, we need to prove one more commutator, which is very important, a relation between the commutators. Suppose we have three operators A, B, C, then it can be proved that this is equal to A, B, C plus B, A, C. You can prove it by taking the left hand side and the right hand side. Suppose you want to take the LHS. This is equal to A, B, C minus B, C, A. How about the right hand side? So the first one is AB minus BC, AB minus BA. Into C plus B into AC minus CA. So that is going to give us ABC minus BAC plus, so you can see very easily that these two cancels out and you are having the same. So one can see that this is very easy to prove the right hand side. So hence LHS is equal to RHS proved. So let us now use this and these two to find the value of Lx, Ly, the angular momentum operator, along the x component, then this is equal to y pz minus z py, and z px minus x pz. So you can write this as equal to y pz z px minus y pz x pz, okay, minus of z py z px and plus of z py x pz. Now we know that if the different components of the momentum commute and the different components of the coordinate commute, that is, it means simply that xy is equal to 0 is equal to yz is equal to zx, and px py is equal to 0 is equal to py pz is equal to pz px. This can be very easily proved since they are the components of the momentum and the coordinate along the different direction. They always commute. They are going to give you the commutator to be 0. That can be proved. And if one proved that, then what we are left with is something like, so y pz z px, this commutes, and y so z py, what we are left with is y pz minus z py and z px minus x pz. So yz commutes, and now we know that also know that x of ex is equal to minus of ih cross, which is equal to y cap py and z cap pz. So using this and this, where we have used a, b, c, okay, and as AD commas commutator ABC plus BSC, I have used this with this 4, not 4, 2, because these two are 0, because y commutes with x, pz commutes with pz, and here also z commutes with z and py commutes with px, because any operator commutes with itself and the commutator of two operator is negative to the commutator of the same set of operator interchanged. And if we assume this to be a, this to be z to be b and px to be c, then I can write the first commutator as this, abc plus bac, okay. And similarly for the fourth one, I can just assume zpy to be a operator, x to be b and pz to be c. So again we can write a b c plus b a c, and now we can again use, we can reverse this in the second step, z y pz px minus x pz z py, again as abc, the same abc, to write this. And from here we can very easily, finally this is left as an homework for you all, to prove that Lx Ly, which is over here, can be written as ih cross y pz minus z py, so which is equal to ih cross z. In the same fashion, one can prove Ly Lz to be equal to IH cross Lx, Lz Lx to be equal to IH cross Ly. So in general, one can prove Li Lj commutator to be equal to IH cross Lk. Okay. I hope this exercise would enrich you in handling the commutator mathematical formalism. Thank you.